morning, everybody. We appreciate your understanding as Benny and I actually kind of balance this presentation today. Benny supports all of our engineering applications with CSX, him and his team, and I'm his business partner in our engineering department, where our group manages all of our linear assets as well as our signals and communication structure as well. So as we wait for it to come up. So I'll just start with a couple of the opening slides. We do work for CSX Transportation. We are a freight-based railroad, Class 1 railroad on the eastern side of the seaboard. We are one of the 4 major carriers in the United States, 2 on the eastern coast. We operate in about 21 to 23 states, 2 Canadian provinces. We also access all of our ports, the Great Lakes, etc. We do interchange with over 200 short line partners. We interchange with all of our Class 1 partners through our western gateways. We have got, here we go, over 30 major classification yards. We actually have over 200 switching yards that we operate our network through. We have over 18,000 carloads a day, over 1,000 trains a day that we're moving. From a physical asset perspective, over 4,000 locomotives, and we own over 62,000 cars. Again, you know, we are vital when you think about this. We're not a passenger railroad. We are a freight railroad. We do touch 2/3 of the United States population. We support all of our industries, which we're going to talk about next, as well as our military. We're very, very, conscious about our carbon footprint and our efficiencies there. And then again, we're safe, environmentally friendly, and we're very, very safe. We touch lots of businesses that you may know today. We move goods to Target, ExxonMobil. Many of our chemicals customers are here today in this forum. We've heard from many of them today. Food and consumer, coal is a huge piece of what we still do today, as well as our intermodal business as well. So let's talk a little bit about what we were and where we are today. We are not your grandfather's railroad anymore. We're not an old, dirty industry anymore. We don't use old technology. We are really becoming state-of-the-art when you think about everything that Pranav already spoke about today. We're leveraging new things like LiDAR to take a look at our clearance. We have automation in terms of what are we looking at to take away the manual work that we do, because anytime that we have anybody touch the ballast line, we have the opportunity for that person to get hurt. So we're always looking for opportunities where we can start utilizing really autonomy to move forward. But most importantly, safety. Everything that we do starts and ends with safety. It's one of our 5 core values. So I'm going to lead it on to Benny to talk a little bit about our safety.
Good morning. So as Chantel mentioned, safety is obviously a top priority for us. Everything we do, we try to do the most safe and efficient method possible. However, accidents can and do happen. In September of 2008 in California, a Metrolink commuter train violated its authority, went through a red signal, and collided head-on with a Union Pacific freight train. There was over 20 people died in this accident. So this happened in September, and the reason it happened was the engineer was texting on his phone. Wasn't looking, missed the signal, went right through it, collision. It happened in September. By the end of the year, government had mandated that all railroads had to implement positive train control. Positive train control has 4 basic capabilities that we have to implement. It has to prevent overspeed derailments, prevent train-to-train collisions, protect on-track workers. These are our engineering forces that are out there maintaining the track, the ballast, etc., and prevent movement through a misaligned switch. This is a safety overlay system. It does not replace the engineer or the conductor on board the train. It merely warns them that they need to take action. If an engineer fails to act, the positive train control system will engage and bring the train to a safe stop. However, if our folks are doing their jobs, PTC would never have to engage. So why do we talk about it? Well, because it's important in terms of the digitalization and connectivity of our railroad to our back office systems. Because positive train control is a system of systems. There are over 100 applications that make up the positive train control system at CSX. Each of these components, each of these systems, see events occurring on the railroad from their unique point of view. So we've instrumented our locomotives, our waysides, and all that feeds into our back office systems in Jacksonville, Florida. Each of these nodes, each of these systems has the capability to record and alert as events occur in real time, to generate alerts to the engineer saying, you need to slow down, you need to stop, you need to do this or that. However, so these provide immediate real-time alerts to our employees, but also those systems can send all that data to our back office systems for further analysis to identify areas of improvement, efficiency, et cetera. Today, we generate over 1 terabyte of information per day, and then we're less than 50% rolled out with PTC right now. But we're going to talk today about the instrumentation of our wayside systems. So let's talk about what a wayside is, just to help get your heads there. When we talk about a wayside, we're talking about the signals and the switches that control train movement. So the signals, they let the engineer know, do you have authority to proceed? What's the speed you're allowed to go? The switch is a physical asset that directs the train from one set of tracks to another. Those switches can either be power switches or manual switches. The one you see in the lower corner here is a power switch. So you can see the switch, the points, and to the right of it, you can see the box. That's the motor. That's the part we're instrumenting. Because of PTC, we have communications now to most of those instruments in the field if they're power switches. So, railroads have been around for well over 200 years, and in some cases, the equipment that's out there is relatively modern. This is a relatively modern 21st century bungalow of signal equipment out on the wayside, okay? Looks like, the bottom box down there, you could kind of say it's almost like a blade computer. You got standard Ethernet ports, et cetera, et cetera. So, 1990s, 2000s. We also have out there, though, older stuff. This is from the 60s and 70s, okay? The previous picture, that was about 40% of what our equipment was in 2011. This was about 40% of it in 2011, okay? Now, however, we do have other stuff out there like this. This was about 20% of our railroad in 2011. This is 1940s and 50s era technology that we had to try to integrate in and instrument for positive train control. Needless to say, this we couldn't really instrument. That all got replaced. We're now back onto mostly modern stuff. But the challenge remains, how do you take these types of systems and instrument them so that you can get that data into a system, generate real-time alerting for safety and efficiency? So we did so, right? We spent a lot of money to do this. We're progressing. But from this, we can take that data that's generated by our field devices, bring it over private secured networks that we have to our data centers in the back office in Jacksonville, analyze it, and identify, like I said, where those opportunities for better asset utilization occur. Because we have the capability, we have the tooling, we just have to get the data in. And because the PTC network allowed us to instrument so much of our network, we've been able to bring that data back and do that analysis. Chantel?
So let's take the example of what Benny talked about, which is what we've done digitizing all of our assets in the field, and how we can apply that now to our business, to the business model. So we run a scheduled railroad. We have to improve our customer service. Again, I talked about safety already as one of our 5 core values. Improving customer service is also one of our 5 core values. What do we have to do to make that happen? Run trains on time. Make sure all of our shipments get to our customer. We give them a commitment, we tell them when it'll be there, and we have to perform to that. Now, what happens when we start to delay the trains? We cannot deliver to our customers, and we have an issue in terms of revenue. We started analyzing what causes train delay. Well, the first thing can be a railroad car. It can break. Axles break, wheels break, bearings are an issue, couplers break. So, small amount of delay, but something that we started looking at. Next area of opportunity are locomotive power. In terms of locomotive power, when the locomotives break down, when we have power issues with them, we cause train delays. We have nothing to move the freight cars with. We actually, while I'm not going to speak about that today, we actually did do some predictive analytics with our locomotive power, where we started analyzing oil within the engine and sending that information back. We've actually had about a 6% improvement in terms of identifying critical failures on locomotives before they happen. So just another great example of what we're doing with predictive analytics. But the largest area that we have of train delay is around switch failures. So Benny showed you an example of those power switches. And when I can't move that switch to realign a train, to maybe I need to pass trains, because we are mostly a single track railroad with sidings where we pass, we stop trains. We could stop passenger and commuter rail that does operate on our railroad, but more importantly, we also stop freight. So when that happens, we can't deliver customer service. There's costs associated with train delay. So we've actually analyzed how much does it cost us when we stop a train, and there's also costs associated with when I need to call out one of my signal maintainers in the middle of the night to go out there and go and fix the train delay in the switch. What can we do? So we asked the question, can we reduce train delay with predictive analytics, particularly in the switch area? So phase one of this predictive model had us go out there with technology and operations research and used 3 key data points that we were looking at. First is around we have to do government-mandated tests and inspection on these switches. Every 30 days, we have to go out there, take a look at the switch, report back, maintain it, fix anything, and then we report it back into our work order systems. We also, switches do fail, we know that today. So we looked at our failure tickets. Anytime we called out a switch maintainer or signal maintainer to go out and look at the switch, we brought in that data as well. And then lastly, we know that the more often you throw the switch, probably the quicker it's going to fail. So we started looking at volume. How many times am I throwing that switch? And all of that model came in, it was pretty basic data, and we built a health score. Green is good, red is bad. We gave every switch a score. And when those scores hit a certain level that were low, we took that information, put it into our signal maintainer's work order, and told them to go out and take a look at the switch. Is it going to fail? Because we want to fix it before a train is sitting there trying to get through it and it's stopped. And we had about an 80% success rate with this. Every time we went out there, we identified that there was a failure, and we got it fixed. And we started seeing a nice reduction in our train delay. This project for us took us a little bit over a year. You know, we went out there, we had to talk to people, we had to go and educate them on what to do, we needed to make sure our data systems were correct. And we did. We saw a nice trend line reduction in terms of what we were seeing. But we wanted to take it a step further. And Benny's system, in terms of PTC, now allowed us to really take a look at real-time data and integrate additional data points into this model. So what did we do? We took a look at sensoring for those switches and those signal boxes. We actually integrated a piece of hardware into the switch motor that looked at current. So, you know, we run batteries and we're looking at the current that's going through that, and the higher the current, more fluctuation that you start seeing, we know that there's an issue, or the longer it takes to throw the switch, we know that there could be an issue. We also had to put in some hardware into the signal boxes in order to transmit the data real time back to Jacksonville to allow for analytics. We did purchase something from a company called MPEC, which was the hardware, and then Centrix, which helped us do some the analytics, pretty basic analytics and visualization. And then we used our own in-house servers and Tableau to do visualization there as well. So we did a pilot, 270 locations up on our northeast territory. This river line here is what we call the river line, is a critical line for us. It moves almost, I would tell you, about probably 30% of our freight goes down that line. You can see here we had to outfit both the signal houses, the switches, the battery voltage. We actually got a benefit out of this as well. We actually identified when a battery was going to fail as well, not just the switch. So that was just kind of an added benefit for us. So what did we see? What you see here is the switch current. So initially you have to get the inertia going, right? So you have high current because the switch is trying to throw, and then it levels out. So this is an example here of a control point on Mohawk subdivision. It's a crossover. So it's 2 tracks. There's a track that crosses in between, and when I need to run a train from line 1 to line 2, we throw the switches. Okay, so 2 switches go at the same time. Well, what do you see here? First of all, switch 1B looks pretty good. Everything is in alignment. The bottom axis that you see here is time in nanoseconds. So we know that there's a standard length of time that a switch should take to be thrown. But switch 1B was looking pretty good. But if you see here switch 1A that is throwing out at the exact same time, we're seeing variations in current, and we're seeing some time issues. We went out and took a look at it. It pinged for us to now say within our new algorithm, there's a problem with this switch. And we looked at it, and it looked great. There was no issues with it throwing until we opened up the signal motor. The signal motor was rebuilt. It was rebuilt in-house, and we used used parts, which is a no-no in our own group. So it gave us indications of not just what is physically going on around the switch, but what's going on within the switch motor. We also took Tableau to start looking at, let's visualize it a little differently. So what you see here is every blue dot is a switch being thrown during the day, during the night, and the red dot is for switches being thrown from 10 until 4 in the afternoon during the heat. Up here, if you look at our 30-day maintenance, this is a 30-day time-bound window right here and on the far side here. This is the same switch. So 30-day maintenance, but if you notice here, right along this piece, we were seeing fluctuations in data prior to the 30-day maintenance. So while the switch current may not have flagged it for us, visualizing this data for us a little bit differently told us that this switch was starting to fail prior to the scheduled maintenance that we had. Just another great example of what we did here. So where are we at now with our phase 2 of these predictive analytics? We've had a 35% reduction in train delay on the territory at which we tested this out, which is significantly better than the rest of our network, both on the Albany division as well as system-wide, and that is accounting for volume-based. We actually reduced while we have more incidences, you'll see here in 2017, we actually did see that that's because there was more oversight. People were going out there to go look at them more. They knew that there were more issues. So they were reporting proactively. Our signal maintainers were taking ownership in their process while they were out there because they knew these were their switches and they wanted them to perform well. We also decreased the amount of time for every time we did delay a train. The train delay time itself was shorter. So we saw not only the fact that we reduced the train delay, but we reduced the overtime at which we were calling people out. And this was in face of a 7% headcount reduction that we had taken over the course of the year. We've had an interesting year, and we did reduce our workforce by 7% on that territory. And you would typically think as you reduce workforce, sometimes your overtime would go up, right? Because you're working people a little bit longer maybe. But in this case, we actually were able to reduce our overtime by 8%. So great application of utilizing predictive analytics, our increased capability of our core network and our communications network to process data faster, and the ability that we just didn't have prior to our PTC implementation.
So where are we at today? Well, based on the positive results we've seen from the pilots we've done in the Albany division, we're going to continue rolling out switch monitoring. CSX's network, our rail network, we kind of look at it as a triangle with Chicago to New York to Florida, Chicago to Florida. At those key switch locations along that triangle, we're going to continue to instrument those switches so that we can identify when they're going to fail, because those are areas of highest utilization and most impact to our rail network. However, we do have challenges to overcome. Number one, the volume of data. As we instrument more and more switches, we receive more and more data, which means that we have more and more to process, right? How do we keep up with that ever-increasing tide of data? And also the algorithms have to improve. Although we've seen improvement in how much train delay and the number of switches instrumented, et cetera, we've got to be able to eliminate false positives and false negatives. Second problem we've got is every time a switch is maintained, you get a new baseline in terms of how well that switch performs or what the data points look like. If you lube the switch, tighten this, tighten that, the amount of throw changes, and now you've got to re-baseline again. That becomes challenging. We've got to tackle that problem. Thirdly, our core business is we're railroaders. We're not data scientists. We have data scientists. We have some very, very bright people, but our core business is railroading, not that. So we're engaging with partners to help us with this. And lastly, as we tell everybody, railroading is an outdoor sport, right? We can't account for the fact that, gee, a piece of ballast, a rock, got in between the switch points, and now the switch points won't close. Or, right now in the middle of winter, snow or ice is there preventing the switch from throwing. Right? Outdoor sport, we can't get around that. Analytics is not going to solve that. But it is reducing our train delays, and that's very positive. So we're going to continue to drive forward. We're going to continue to use these sensors and the analytics to get better asset utilization and more efficiency and productivity out of our assets, and help keep our folks focused on what they need to be doing, which is moving our freight. Thank you.
Thank you.